Okay. Online students, can you hear me clearly? Online students, can you hear me clearly? Please confirm with a message. Online students, can you hear me clearly? Sure. A tute. Online students, can you hear me clearly? Okay. Sounds. Okay. So let's start today's session. Today we have to start waves, right? Today we are starting with waves, right? Okay. So to continue, right? Did you get two tutes? There are two tutes. One is the main one, and the other one is the additional tute. That means you may need an additional tute that is meant to be written in the book. Okay, that is meant to be written in the book. So the plan is like pay attention, stop talking. So the plan is since it takes a lot of time to write things in the note, I printed that part, but ideally you should put that into the book later, okay? So within this week, you have to write down this in the book. So for online students, we have delivered a lot of tutes, but if you haven't received the tutes, go check the group. There you can find information required to get the tutes delivered. If you don't have the tute, for now, you can get the tute from the resources section of the website, okay? Resources section of the webinar, okay? In the Zoom webinar, there's a tab called resources. From that resources section, you can get the tute, okay? Clear? From the resources section, you can get the tute. Okay. And if you can't find that, I think tutes are available in the group too. But if there's any kind of issue, if you can't find the tute or if there's any other issue, just inform in the chat, okay? Yeah. So online students have received only the main book. Other one is given as a PDF because anyways you have to write it in on the book, okay? So it's just there for reference. I mean, otherwise I have to wait until you write everything. Pay attention. Otherwise I have to wait until you write everything. So just to like save some time, I have printed that for the physical class, and online people can get the PDF. So anyways, after today's class, you have to like rewrite them on your book, okay? So that is mainly the note. So no need to get that delivered, okay? The extra tute. Okay, so let's start with today's lesson. Today we are discussing about waves and oscillation, okay? Today the topic is waves and oscillations. So in this lesson, we mainly discuss about like basically oscillations and waves, okay? Oscillations and waves. So like there are different types of waves, like waves on water. Sound is a wave, okay? Sound is a wave coming to your ear. And like the electromagnetic waves, okay? Like me talking goes to that receiver as an electromagnetic wave. And there's thousands of types of different waves, right? Clear? There's thousands of different types of waves. But when we talk about all these waves, okay? When we talk about all these waves, like the fundamental component of all these waves, okay? The fundamental component of all these waves is simple harmonic motion. What is simple harmonic motion? Simple harmonic motion is a type of like motion that a particle can have which has a specific pattern. For an example, I mean, pay attention. Take a wave like this, wave in a string, or waves you see on the sea. Okay, the waves you see on the sea. These waves are not something going like this forward, okay? This wave doesn't mean that something actually moves forward. That means particles are moving up and down accordingly. Okay, particles are moving up and down accordingly. Got the idea? I mean, if you have a string like this, okay, just a normal string, you send a wave like this. You send a wave like this. Then you can see a wave moving forward like this, okay? Then you can see a wave moving forward like this. But actually the string is not going anywhere, right? Actually, the string is not going anywhere. Okay, string is not going anywhere. What actually happens is the particles of the string goes up and down. See, particles of the string goes up and down such that we see it as a wave. Okay, particles of the string goes up and down. Clear? Particles of the string goes up and down such that we see it as a wave. Got the idea? So in a string, okay, in a string, when a wave goes like this, what actually happens is the string is not actually going anywhere. Okay, the string is not going anywhere. Just particles of the string moves up and down such that I can see a wave. Okay, clear? So waves are just a transfer of energy in this direction as a result of the motion of single particles. And these single particles are not moving anywhere. Okay, clear? These single particles are not moving anywhere. Okay, they are just going up and down accordingly such that I can see it as a wave. Okay, clear? Kind of illusion. Okay, now then the motion of this one single particle, okay, the motion of this one single particle, if I take that, it is just a motion like this. There's a center, it goes up and it goes down, goes up, stops, goes down, stops. It goes in a motion like this. Okay, it moves in a motion like this. Clear? Okay, it moves in a motion like this. This specific motion that this particle follows, okay, this specific motion this particle follows, we call that a simple harmonic motion. Okay, the specific motion this particle follows, we call it a simple harmonic motion. So when you talk about a simple harmonic motion, there's a center of oscillation. There's a center of oscillation. Then it goes into a certain direction. It has a certain velocity at the center. It has a certain velocity at the center. Then when moving away from this center of oscillation, it slows down. Okay, when moving from this its center of oscillation, it slows down and ideally stops. Ideally stops. Velocity becomes zero. Okay, velocity becomes zero. Okay, then it turns into the opposite direction with the same velocity of zero, then moves in the opposite direction like this. Then again gain enough velocity here such that it moves down, then again slows down and stops here, slows down and stops here, then starts returning back. This keeps happening. This is a simple harmonic motion. Okay, harmonic motions are things that repeats. Okay, it's just a simple thing. Harmonic motions are motions that repeat. Okay, harmonic motions, I mean even the earth moving around sun is a harmonic motion. Okay, this is a different kind of motion. This is a special type of repeating motion. We call it a simple harmonic motion. Okay, this is a special type of repeating motion and we call it a simple harmonic motion. Okay, so here in this simple harmonic motion, there's a, for a motion to be anything going up and down is not a simple harmonic motion. Okay, anything moving up and down is not a simple harmonic motion. There's a bunch of rules a simple harmonic motion should follow, a fundamental equation that a simple harmonic motion should follow. Okay, what is this fundamental equation? The fundamental equation is A is proportional to X. That is the fundamental equation. That means the acceleration felt by the simple harmonic motion is proportional to its displacement from the center of oscillation. Clear? Acceleration felt on a particle in a simple harmonic motion is proportional to the displacement from the center. Clear? That means definitely it feels the acceleration in opposite direction. Okay, clear? Definitely it feels the acceleration in opposite direction for sure. Why? That's why it slows down when it goes up. Okay. This acceleration it feels should be proportional to the displacement. So further it goes, higher the acceleration. So more tendency to stop. As a result, it stops here, then returns to the opposite direction. Okay. So this whole motion is a result of this behavior. Okay. This behavior. And if k is a constant, I can tell it is a equals minus kx. It has the type of a equals minus kx where k is positive. Okay. Where k is positive. Clear? Why? If k is positive, acceleration and displacement are vectors. So when it moves up, acceleration is downwards. So the displacement and acceleration are opposite. Okay. Displacement and acceleration are opposite. Clear? So as a result, this k should be a, if when k is a positive value, this should be negative. Okay. This should be negative. Clear? So that is the equation that we need. Okay. That is the equation that we need to keep a simple harmonic motion happening. Okay. Any motion that follows this equation, that is a simple harmonic motion. Okay. Clear? Any motion that follows this behavior, it is a simple harmonic motion. Okay. Then moving forward from here, like after this point, we are going to analyze the actual behavior of a simple harmonic motion. That means we need to know, before understanding waves, we have to know everything about simple harmonic motion. How the acceleration changes, how the velocity changes, how the displacement changes, how everything changes with time, we have to understand. Okay. We have to understand how everything changes in a simple harmonic motion. Okay. So from this point onwards, our target is to analyze and understand the actual behavior of a simple harmonic motion. Okay. Then that we can so I need an equation for the behavior of the acceleration of a simple harmonic motion with time. That means I need an equation for A from time. I need a equation for x with time. I need a equation for the velocity v with time. I need to create everything. Okay. And the problem is simple harmonic motion is not, it's not easy to analyze a simple harmonic motion. Why? What is the reason? It's not easy to analyze a simple harmonic motion after this point, because this is the fundamental definition of a simple harmonic motion. But after that point, okay, we need integration and differentiation to keep moving to these equations. That means when you have a relationship of acceleration, you integrate to get the velocity. You integrate it to get the displacement. So integration and differentiation is required for further analysis of simple harmonic motion. Okay. But the problem is, in our syllabus, we don't have this integration and differentiation kind of stuff. Okay. In our syllabus, we don't have this integration and differentiation. Okay. So we come up with a simple solution. Okay. We come up with a simple solution. That solution is, we find an equivalent motion that we already understand. Okay. We find an equivalent motion. Okay. We come up with an equivalent motion that we already understand. What is this equivalent motion? We tell that a simple harmonic motion is the one-dimensional version of a circular motion. We tell that a simple harmonic motion is the one-dimensional version of a circular motion. That means if a particle moves in a circular motion, if a particle moves in a circular motion with a constant angular velocity, if a particle moves in a circular motion with a constant angular velocity, if you restrict this to one dimension, that means you put a wall here, you put a wall here, and you turn on a torch from this side. You turn on a torch from this side. Then what happens? You can see the shadow. You can see the shadow of this particle, right? You can see the shadow of this particle here. So when this particle is here, the shadow of this particle will be here. The shadow of this particle will be here, okay? When this particle is here, the shadow of this particle will be here. When it is here, the shadow is here. Like that, with this particle, when this moves with a constant angular velocity like this, when this moves with a constant angular velocity like this, with this particle, the shadow will keep moving, okay? With this particle, the shadow will keep moving. When it is here, the shadow is here, okay? Like that. What is that? What have I done here? I have actually restricted it into one dimension, right? I have restricted it into one dimension. That means when the circular motion happens like this, its shadow goes like this, right? Clear? When the circular motion happens like this, its shadow goes like this, right? Clear? And we do a small prediction. We tell that we do a small assumption actually. We do a small assumption and tell the movement of this shadow, if this is a constant angular velocity, the movement of this shadow is a simple harmonic motion. That is an assumption that we make, okay? So what we are going to do is we are going to move forward with this assumption, okay? We are going to move forward with this assumption. Then later we are going to prove it, okay? We are going to move forward with this assumption, create all the equations, then later we are going to prove it. So what is the assumption? I mean, if I don't have to go through this drama if we had integration and differentiation in the physics syllabus, okay? So all the problems, all the troubles are here, okay? All the troubles are here because we don't have required maths, okay? We don't have required maths, okay? So this is just an assumption, okay? Just an assumption. You remove one dimension from a circular motion and restrict it into single dimension. This is a two-dimensional motion, right? Circular motion is a two-dimensional motion. You remove one dimension out of it, okay? You remove one dimension out of it, then you have a simple harmonic motion. That is the idea, okay? Just an assumption, okay? Just an assumption. We'll see whether it's correct or not. Now, so for the people who haven't done circular motion kind of stuff, a quick review of the things that you, I mean, today, to understand today's content, you need some mechanics, okay? But it's only today. From next week onwards, we are moving to the waves part. From the waves part, it is an entirely new part. That means you don't need your knowledge from mechanics, okay? You don't need your knowledge from mechanics. You need your knowledge from mechanics for today's content. Pay attention. You need your knowledge from mechanics for today's content. But after that, for next week content and the content after that, we don't need, okay? We don't, I mean, not the next week, just the next week. Everything after this point, we don't need mechanics until we finish optics lesson. So for the people who haven't done mechanics properly, okay, just a message. For the people who haven't done and who haven't understand mechanics properly, today it's not going to be easy. But from next week onwards, it's not a big issue. You don't need mechanics for anything after that point. For like 2-3 months, then you need mechanics to a very great extent after that point. That means from next week onwards, you don't need mechanics. But after 2 months, you need a lot of mechanics, okay, for the lessons after that. For the waves lesson, after today, and for optics lesson, you don't need the knowledge of mechanics. But after 2 months, you need an extreme level of mechanics. So what you should do is, today, yes, try to somehow understand. From next week, it's not going to be an issue. But within the next 2 months, try to go through the content again, do questions, try to finish mechanics parts, do whatever possible, okay? Do whatever the thing that you can do and try to be good at mechanics within the next 2 months. For because for the next 2 months you don't need mechanics. That's why. Okay, within those 2 months you have to somehow be good at mechanics. After that we start fields. Okay, after that we start fields, gravitational fields, static electric fields, magnetic fields. After the optics lessons, you won't understand anything in fields if you don't understand mechanics. Okay, clear? So it's only today. So like a quick recap of things, we know that if a particle moves in a circular motion, if a particle moves in a circular motion of radius r, if its angular velocity is omega, okay, this particle will have a linear velocity everywhere. This particle will have a linear velocity. Okay, this particle will have a linear velocity. Okay, this particle will have a linear velocity, and that is equal to r omega. That we know, right? That is equal to r omega. That velocity can be taken by r omega. Omega is the angular velocity. R is the radius of the path this moves. Okay, clear? Then the time it takes to complete a full circle. Time it takes to complete a full circle, we call it the periodic time, capital T, right? Time it takes to complete a full circle is T. That I can write using what? That I can write using one angle theta over omega. So what is one full rotation? What is the angle for one full rotation? Angle for one full rotation is 2 pi radians. Angle for one full rotation is 2 pi radians. Then you divide it by what? Then you divide it by omega. So T can be taken by 2 pi over omega. Okay, the periodic time can be taken by 2 pi over omega. Then frequency of this motion means how many oscillations per second. Frequency of this motion means how many oscillations per second. Okay, how many oscillations per second, which means I can write 1 over T means 2 pi over omega. 2 pi over omega. 1 over T means 2 pi over omega. Then I'm going to get F equals omega over 2 pi. F equals omega over 2 pi. Then we are going to get omega equals what? Omega equals 2 pi F. Okay. We are going to tell that the omega equals what? Omega equals 2 pi F. Okay. Omega equals 2 pi F. Clear? That is the equation for omega. Okay. The angular velocity. Okay. So these equations we may need to understand this stuff. Okay. Clear? Okay. So here, let's think that, so this is going to be the center of oscillation. This is going to be the center of oscillation. And so here, for this simple harmonic motion, if this is the center of oscillation, the maximum distance it travels from the center, we call it the amplitude. Okay. Maximum distance it travels away from the center, we call it amplitude. Okay. Maximum distance it travels from the center, we call it amplitude. So here, what is the amplitude then? What is the amplitude in this scenario? It is going to be this end and this end, right? So this is going to be the amplitude. Okay. This is going to be the amplitude. Okay. So as a result, the radius of this circle, see, the radius of this circle should be equal to amplitude, right? Clear? So the idea is when we are using a circular motion or a circle to understand a simple harmonic motion, the radius of that circle, the radius of that circle should be equal to the amplitude of the simple harmonic motion that we are going to understand. Okay, clear? Radius of the chosen circle should be equal to the amplitude, should be equal to the amplitude of the simple harmonic motion that we are analyzing. Got the idea? Okay. Then, so I have chosen the amplitude A. Okay. It is equal to the, I have chosen the radius. It should be equal to the amplitude of the simple harmonic motion that I'm going to analyze. Okay. Then moving forward, let's try to understand the displacement equation. Now, let's think that it moves here. Let's think that the particle moves here. Okay. The particle moves here. Then this angle is theta. It moves an angle of theta. Okay. Let's think that it moves an angle of theta. Then, if it starts here at t equals 0, if time here is t, if time here is t, I can call this theta. Omega equals, it is angular velocity, so angular velocity equals angle over time, right? Angular velocity equals angle over time. So theta equals what? Theta equals omega t. Okay. Theta equals omega t. Okay. So the angle is going to be equal to omega t. Now, what is the displacement of this particle? What is the displacement of this particle? What is the displacement of this particle from the center? Displacement of this particle from the center is x. Okay. Displacement from the particle, the displacement of this particle at the moment from the center is x. Okay. X. How can I get this value x? Okay, pay attention. Pay attention. So now, this is the displacement of the particle from the center, right? This is the displacement of the particle from the center. It is x. Okay. Now, that x is equal to this, right? That x value is equal to the x value here. See, this is the x that I need to find. Okay. Clear? So I can write what? I can write the radius of the circle is a, amplitude. Okay. Radius of the circle is a, amplitude. So I can write cos theta equals what? Cos theta equals x over a, right? Cos theta equals x over a. Clear? Cos theta equals x over a. So x is going to be what? A cos theta, which means a cos theta means omega t. A cos omega t. X equals what? X equals a cos omega t. Clear? Okay. So this is the equation. So as I mentioned, I need a certain equation for the displacement with time, right? I need a certain equation for the displacement with time, and that equation is x equals what? A cos omega t. Okay. X equals a cos omega t. Okay. Is this clear? So now I have, okay. Now everything is based on an assumption. This circular motion restricted into one dimension gives me a simple harmonic motion. Just an assumption, okay? I don't know the correctness, but based on the assumption, I'm going to continue, okay? I'm going to continue based on the assumption, okay? That's all. Clear? Now I have an equation for x from t, okay? Then the next one, if I need the velocity, how can I get the velocity? Now see this. At the moment, the velocity of this motion is in this direction, right? Velocity of this motion is in this direction, right? It's a tangential velocity always, okay? It's a tangential velocity always. Clear? Then, if this is theta, what is this angle? If this is theta, what is this angle? If it is theta, we can tell that if this is theta, okay? If this is theta, this is going to be 90 minus theta. Then this is again theta. Clear? Now, when this one is moving like this, the velocity of its shadow is going to be this, right? The velocity of its shadow is going to be this, right? Clear? Velocity of its shadow would look like this. Clear? So I need to find that. So how can I find that velocity? That is the velocity of this simple harmonic motion. So that is equal to the horizontal component of this velocity, right? Shadow has the horizontal component of this velocity. Clear? The shadow has the horizontal component of this velocity. And what is the velocity of this one? It's going to be always r omega, right? Clear? It's going to be r omega, okay? So here also the velocity is then r omega. So I need the sine theta component of r omega, right? I need the sine theta component of r omega. Clear? That is going to be the velocity of the shadow. Okay? So the velocity would be what? Velocity would be r omega. R omega is the velocity here, sine theta. R omega sine theta. Clear? Clear? If I choose directions, let's choose this direction as the positive one. Let's choose this direction as the positive direction. Then this displacement is in this direction. So it is positive. At the moment, the velocity is in this direction. Okay. So it's going to be negative. It's going to be negative. Okay. It's going to be negative. So this is the equation for the velocity. This is the equation for the velocity. Clear? Then what about the acceleration? What about the acceleration? We know that to keep a circular motion active, we always need a acceleration towards the center. Okay? To keep a circular motion active, we always need an acceleration towards the center. Which is what? Which is centripetal acceleration, which means r omega squared. Can you remember? A circular motion always need an acceleration towards the center, and we call that what? We call that r omega squared. It is the centripetal acceleration. So here also, the acceleration of this particle would be towards center, okay? Acceleration of this particle is towards center, okay? Acceleration of the particle is towards center, and it is r omega squared. It is r omega squared. Acceleration towards the center is r omega squared. What I need is the acceleration of the shadow. Acceleration of the shadow is in this direction, which means the horizontal component of this acceleration, right? Clear? Which means the horizontal component of this acceleration. Clear? So it is going to be, the acceleration is going to be, so its direction is this. This horizontal component is in this direction. So if this is the positive direction, something in this direction is going to be negative. Something in this direction is going to be negative. So acceleration is minus, this is r omega squared. This is r omega squared. This is r omega squared cos theta, right? If this is theta, this component is going to be cos theta. So it is minus r omega squared cos theta. Clear? So that is going to be the acceleration. Okay? That is going to be the acceleration. Okay? This is the equation for the acceleration. Clear? Now what? Now what? Here r is a, okay? R radius is a, okay? Here, throughout the equation, the radius I have chosen is a, okay? Radius of this circle is equal to the amplitude, right? So I won't write two symbols for that. Instead of r, I would write a, okay? Clear? Instead of r, I would write a, okay? Now what? Now what? Now we have to check one thing. This is the acceleration. So if I try to do a small modification, acceleration equals minus omega squared. Acceleration equals minus omega squared a cos theta. Here also in both cases, theta is equal to omega t, okay? Theta is equal to omega t. That means theta is going to be the angle you move within time t. So theta is going to be equal to omega t. Angular velocity into time gives you the angle. Okay. So theta is going to be omega t. Theta is going to be omega t. So now here I get a equals minus omega squared a cos omega t, a cos omega t, a cos omega t, which is equal to minus omega squared, which is equal to minus omega squared. What is a cos omega t? A cos omega t means x, right? A cos omega t means x. Clear? So what is this? A equals minus kx should be the equation of a simple harmonic motion. Can you remember? We started with that assumption. A equals minus kx should be the format of a simple harmonic motion, and this actually follows that. That means the moment of this shadow, okay, the behavior of this shadow actually follows the behavior of a simple harmonic motion, so no big issue. Okay, clear? So my assumption is correct. So we are gonna keep proving things, and at the last step we are gonna prove that the assumption is actually correct. Okay, so actually the shadow of a circular motion gives us a simple harmonic motion. Clear? Okay, so like if you take your tute, like things are a bit different in your tute. Okay, things are a bit different on your tute, and your tute have a different version, so you don't have to write anything yet. I'll tell you when you have to write things. Okay, let's move to the other version. So this is one version. Okay, this is one version of it. Then let's move to the other version. Okay, let's move to the other version. Okay, let's move forward. Let's move forward. Another version, I mean, that's not the only way possible. I mean, if you get a circular motion and turn on the torch from this side, turn on the torch from this side, on this wall also you will get a simple harmonic motion, a similar scenario, right? So a simple harmonic motion means, I mean, popular simple harmonic motions, the things we know, the motion of a pendulum, motion of a pendulum, motion of a spring. You connect something to a spring and give a small displacement, then it is a simple harmonic motion, okay? So all these motions are simple harmonic motions. So what actually happens is, if you need to understand, okay, if you need to understand the motion of a, let's assume motion of a spring, okay, let's assume that you need to understand the motion of a spring, okay, pay attention. Let's assume that you need to understand the motion of a spring, okay. So you can't understand the motion of a spring due to the lack of mathematics in our syllabus, okay. So the solution is, you first check the amplitude of this motion. How can you check the amplitude of this motion? I mean, if you move this until here, if you move this until here and release it, if you move it until here and release it, then it's going to move in this range, okay, clear? So if you give an initial displacement of A to that, if you give an initial displacement of A to that and release it, it's going to move in this range, okay, clear? So the first thing is, when you know the amplitude, you draw a circle, with an equal radius. You draw a circle with an equal radius, okay? That's how we choose the radius of this circle, okay? That's how we choose the radius of this circle. Then this has a certain speed. This one should be going accordingly, okay? This one should be going accordingly. Clear? I mean, we don't get a simple harmonic motion for the circle, okay? We have a simple harmonic motion. To understand, we need a circle. So we look at the simple harmonic motion and choose the proper circle for that, okay? Clear? I mean, you don't get a simple harmonic motion for a circle. What you have is a simple harmonic motion. It doesn't come with a circle. Then you draw a circle for that to make sure that you understand that. So the first step of understanding this circle is, you get the radius as the amplitude. Then you have to choose the proper omega, proper angular velocity, such that they move together like this, okay? Clear? Otherwise, when this guy goes like this, if this one goes like this, then it's not the circle for this simple harmonic motion, okay? Clear? This thing can't move faster. It should be predicting the simple harmonic motion properly, okay? Clear? So you have to choose proper omega. Choosing the proper omega, we are going to do it later, okay? We are going to do it later. As the next step, we are going to find omega. For now, let's put it as omega. Okay? But the actual thing is, when you have a simple harmonic motion, you should find the omega value for that. Okay? Clear? So anyways, if it starts here, see, when you turn on the torch, it's here. Then it moves an angle of theta. Theta is equal to, again, theta is equal to what? Theta is equal to omega t. Okay? Then this is the motion, clear? And this velocity is going to be r omega. If this is theta, this is going to be theta. If that is theta, this is theta. Okay? Then we have a centripetal acceleration, r omega squared. Okay? But now, and this is the displacement. This is the displacement at the moment, x. Clear? So now everything is vertical, okay? Everything is vertical. So x is going to be, here x is going to be, radius is the amplitude, right? A sine theta, okay? Initially x was a cos theta. In this case, x is a sine theta, okay? In this case, x is a sine theta, clear? A sine theta, x is going to be a sine theta, clear? Here x equals a sine theta, which means x equals a sine omega t. A sine omega t, clear? X equals what? A sine omega t. Okay. Then what's next? Next, velocity. Let's choose this direction as the positive direction. Let's choose this direction as the positive direction. Then the velocity is going to be, velocity is r omega, but I need the vertical component, right? Shadow has the vertical component, clear? Shadow has the vertical component now. So it is r omega cos theta, clear? It's going to be r omega cos theta. Here r is a. R is a. So a omega cos theta. Theta is omega t, okay? Theta is omega t. Then the acceleration is, this is r omega squared, okay? Acceleration is r omega squared, and I need the vertical component, okay? Why? The shadow has the vertical component. So it is going to be r omega squared, the centripetal acceleration. Centripetal acceleration is r omega squared sine theta, clear? But it is going to be minus, why? See, this I chose as the positive direction. This I selected as the positive direction, but this is negative, right? Clear? R omega squared sine theta is negative. See, they are opposite. Clear? They are opposite. So it is minus r omega squared sine omega t. Okay? Minus r omega squared sine omega t. Clear? Clear? So again, what is r? It is the amplitude. Okay? R is the amplitude. Okay? So we are going to get a equals minus omega squared. A equals minus omega squared. A sine omega t. What is a sine omega t? A sine omega t is x. So a equals minus omega squared x. With that, we prove that this follows a equals minus kx format. Okay? This follows a equals minus kx format. Clear? So now displacement is a sine graph, right? Displacement with time is going to be a sine curve. Okay? Displacement with time is going to be a sine curve. Okay? With the maximum and minimum with plus a and minus a. Clear? Plus a and minus a. Then velocities velocity is going to be a cos curve here, right? It's going to be a cos curve. Okay? Velocity is going to be a cos curve. So a cos curve would look like this. Clear? What is the maximum value that cos omega t can get? What is the maximum value that cos omega t can get? Maximum value of cos omega t is 1, right? Maximum value of cos omega t is 1. Okay. So it is going to be a omega n minus a omega. Clear? It's going to be a omega n minus a omega. Clear? Maximum value of cos omega t is 1. Then acceleration is going to be a minus sine graph. Okay. Acceleration is going to be a minus sine graph. Okay. So properly pay attention why even, I do revision classes. So even in revision classes, like we have to teach simple harmonic motion again and again because it is a major part that students don't usually understand. Okay. Yeah. Another major part that students don't usually understand. So pay attention. Okay. So the acceleration is going to be a minus sine graph, right? Acceleration is going to be a minus sine graph. Clear? So it's going to be a omega squared and minus a omega squared. So in the additional tube given to you guys, it's just shown as a sine graph. That's what is required. But just correct it into a minus sine graph. Minus sine graph goes like this. Even a normal sine graph is okay. But it's perfect if it is a minus sine graph. You can see in the additional tube given, online student, hope you can find it in the resources section of the webinar. There's a special section called resources in the webinar. See, you have these tables, okay? So here, pay attention, everything is connected with each other, okay? Here, everything is connected with each other properly. That means the spring, pay attention, its circle, and these lines show the relationship, okay? And its own displacement, okay? And its own displacement. So everything is properly connected here, okay? Everything is properly connected. Clear? Everything is properly connected with each other. So the reason I gave this, because I can't wait until you guys draw this thing, okay? But the thing is, within this week, these things should be converted into your book, okay? This is the note that you have to write, but I don't like to wait until you write. That's why I printed this, okay? So this must be in your book within this week, okay? Clear? I just can't wait a lot of time until you draw this diagram. I mean, for you guys, it takes like 2-3 minutes to draw a circle. So I mean, if we have to draw this in the class, that's all I can do today. So that's why I printed it, okay? That's why it was not sent to online people. Just get the PDF and draw everything on your book, okay? Physical class students, get the PDF, go home and draw this properly, okay? It's a must because these things you have to remember and you remember by doing that, okay? Okay, so definitely this is, don't keep this, plot, convert things into your book and throw this, okay? That is the idea. So is it clear? Okay. I mean, I am really thoughtful about time, okay? So, I mean, just don't ask. I have a good result, okay? I have results better than everyone, okay? But I'm not going to waste your time talking about it, okay? Then your results would go down, okay? So you can check the group. Our marketing people do the rest, okay? So we have a separate bunch of marketing people. They do the rest. You will see the results, okay? We have better results than any English medium class in the country. But I'm not going to waste your time talking about it, okay? So let's move forward. Okay, so don't ask. You can check. Check the group and all. Okay. So pay attention, pay attention. Now it's okay if you need to complete your tube. That means some stuff like this are not written. They are actually written somewhere, okay? But I mean, if you need to take few minutes and complete your tute, yes, do that, okay? But later, write the proper tute on your book, okay, within the week. If you need to write some additional stuff on your tute or on your book, take time and write that, okay? But you don't, I'm not going to give time to draw all these stuff, okay? Clear? That you can draw later. Drawing graphs and everything, you can do it later. But if you need to complete your tute, okay? If you need to complete your tute of it, just do that, okay? I mean, sometimes we are judged to be having a marketing team. We have a separate marketing team. So sometimes it's mentioned as a bad thing. But I think having a marketing team is good. Then you don't have to do the marketing yourself in the class. You can teach. The people will look after the marketing, right? So that's why I can teach efficiently. Sometimes, like I have seen, like some teachers mention about our class, okay, these guys have marketing people. That's what they do. They perform. I mean, we don't have a marketing people. Then buy a marketing team. What the hell are you doing? You just go and teach. Okay. I mean, sometimes we have seen that. Sometimes we get that complaint from sometimes like very senior teachers. Okay, these guys are doing a bunch of marketing, a hell lot of marketing. What the hell? They have a huge marketing team. Yes, have a marketing team. You better buy yourself a marketing team, right? Then you can go to the class and teach. Okay, that's the whole point of having a marketing team. So I mean, can't explain this to some seniors people. Okay, here, quickly, write down if you need something. Okay, quickly write things, okay? Quickly write things. This is just for the addition, okay? Just if you need to add something into your tute, just do that. Don't try to write the note now. You can write the note later, okay? Okay, pay attention. So this is what you have on your tute, okay? I started with that to explain something. Displacement is not always sign. Velocity is not always cos. Acceleration is not always minus sign, okay? See here? Here, displacement is cos, velocity is minus sign, acceleration is minus cos. Things can change. Things can change based on what? Based on the starting position of the simple harmonic motion. See, this is starting from its end. See, this is t equals 0. So the simple harmonic motion is starting from its amplitude. Here, the simple harmonic motion is starting from its amplitude. Then moves towards the center, then to the other amplitude, then move towards the center, then to the other amplitude. Okay, clear? Okay. So that's what happens here. Here, this is t equals 0. This is t equals 0. Okay, and it's starting from here. This is t equals 0. It is starting from here. So it's starting from the center of oscillation, then it goes away from the center of oscillation up and down. Okay, then it goes away from the center of oscillation up and down. So this is starting from the center of oscillation, then it is sine. Like that, the equations changes based on the starting location. So starting location can be an entirely random point too. Okay, starting location can be an entirely random point too. Then equations may change a bit. Okay, clear? So you can't remember, okay, this equation for this equation for that. No, you just know the theory. Okay, know the theory and how it happens. Okay, just try to understand the theory and how it happens. Then you can, whenever required, you can derive things up. Okay, so if you need to, this is not included in your extra tune. So if you need to write anything, quickly put a note. Okay, I'm not going to give a lot of time. I mean, we have close to 700 or 800 students in the 28 batch starting, and you guys know how I teach at the beginning, right? Without a marketing team, we can't give 800 at the beginning. You know what happens when I start teaching, right? In the first few days. So we can't retain 800, 900 students the way I teach in the beginning, right? If you were there at the beginning, we can. So it's all about the marketing team. Even in Ratnapura, we have close to 600 to 700 students now. It's my just second year in Ratnapura. In the second batch, in the first batch, we had like 40 students. Ratnapura first batch, we had like 40 students, and this is the second batch. We have close to 600 students in the second batch. So the same story, you know how I teach at the beginning. You can't keep 600 students at the beginning if the marketing isn't good. Yes. For the exam, they may ask everything. Okay, so you have to know everything. This is a very important part. This is a very important part. Okay, other graphs. Other graphs. Now, let's move forward. Anyone need to write anything here? You're done with everything? Quickly write down if you have to put anything onto the book. Quickly, I'll give 1 minute. Okay, then let's move forward. Now about other graphs. It's a bunch of graphs, okay? You have to remember. Not actually remember, understand. So now, correct this graph, okay? Correct this graph. Convert it into a sine graph, minus sine graph, not a sine graph. Convert it into a minus sine graph. Okay, in your extra tute. Okay. So moving forward, okay? Moving forward. It's better if we can. I'm gonna create more equations actually, okay? Pay attention. I'm gonna create more equations. Sometimes they give us the displacement. Sometimes they gives us the displacement and ask for the velocity. So in a question, if they give us the displacement and ask for the velocity, what we can do is we get the displacement, solve this, find t, then put that t here and get the velocity. But it's just a lot of work. So it's good to create a direct relationship. Between v and x, okay? Clear? It's good if we can create a direct relationship between x and v. So how? This is sine omega t. This is sine omega t. Sine omega t equals what? Sine omega t equals x over a, right? Sine omega t equals x over a. X over a. Then cos omega t. Cos omega t equals v over a omega. Cos omega t equals v over a omega. Now what? Sine squared omega t plus cos squared omega t equals 1, right? Sine squared omega t plus cos squared omega t equals 1, right? Sine squared theta plus cos squared theta is 1. Clear? That you know, right? Then you get, what is this? X over a squared plus this is v over a omega squared equals 1. Okay? X over a squared plus v over a omega squared equals 1. Then we get x squared over a squared plus v squared over a squared omega squared equals 1. Then we can get, what I need is to find v, velocity. So we get omega squared a squared minus x squared. I take this here. I'll show you the steps. V squared over a squared omega squared equals 1 minus x squared over a squared. Then a squared minus x squared over a squared. Then this a squared and this a squared cancels out. Then I'm left with, v squared over a squared omega squared equals this a squared minus x squared over a squared cancels out. Then v squared equals omega squared a squared minus x squared. Then v equals omega square root a squared minus x squared. Okay, this is an equation for the velocity. Okay, these are also included in your tutor. Okay, in the upcoming pages everything is included, not in the exact order that I teach. Okay, but if you need, you can take a minute and write these things down, and later create a proper note by yourself. Okay, create a proper note by yourself. Quickly write down things if you need to complete your tute. ask if you have questions until now. Okay. Okay. Let's move forward. Uh, uh, so now we have an equation with velocity and displacement. So the other set of graphs. it's good to see how things changes with displacement. You will understand when we do questions and when we learn about waves later, you will understand why all these equations and everything, okay? There's a purpose for these things. For now, just learn it as facts. So now, like, it's good to learn the behavior of things with the displacement too. That means now I have the graphs, I have equations, and I have everything. I have graphs, equations, and everything with time, okay? With time, okay? It's good to get these things, okay? It's good to draw these things with displacement too, okay? That means this is how things changes with time. It's good to draw or know how things behaves with displacement. That means the distance from the central location. How things changes with the distance of the central location. So take a simple harmonic motion. This is the center of oscillation. This is the center of oscillation. This is the center of oscillation. So, and it's going to move in this direction and in this direction, okay? It's going to move in this direction and this direction. Let's consider this as the positive direction. So this is the positive amplitude. This is the negative amplitude. Okay, pay attention. This is the positive amplitude and this is the negative amplitude. Then the velocities would look like this. The velocity graph with displacement. Velocity graph with displacement would look like this. You have the maximum velocity here. You have the maximum velocity at the center. And the velocity decreases with displacement, okay? Velocity decrease with displacement, okay? Here also velocity decrease with displacement, okay? And you have what? You have another side of this. Why? You have a positive side for velocity and a negative side for velocity. Why? Here, this particle, there's an instance where this particle is moving in this direction, and on the way, at the same point, it moves in this direction. So for the same displacement, okay, for the same displacement, we have velocities in that direction and velocities in this direction. That means a positive velocity and a negative velocity. Clear? We have a positive velocity and a negative velocity. Clear? So this is the idea. This is velocity. And if it is speed, it's only positive, right? If it was speed, no big issue. It's only going to be positive, okay? Speed is only positive, okay? So this is actually the graph of this equation, okay? This is actually the graph of this equation. Clear? So this is how velocities behave, okay? This is how velocities behave. And in your additional tute, even they are linked with the main graph, okay? You can see in the tute given to you guys, they are drawn in this direction. Why? They are drawn in this direction, like this. Clear? Clear? Why? The initially drawn simple harmonic motion is happening in this direction. So based on that, how this changes. See? Based on that, how things changes. In the tute given, it tries to predict how things changes. Okay? Clear? Okay. You don't have to go to that extent to create your note. If you understand, it's okay. Clear? Did you understand up to this point? Pay attention. So the velocity behaves like this. It stops here. It stops here. It has the maximum velocity here and the negative maximum velocity here. Clear? Why do we have a positive side and a negative side? At every location, it may be going in this direction or it may be going in this direction. Clear? At every location, it may be going in this direction and it may be going in this direction. Clear? Moving forward. moving forward. The energy, the last part, the behavior of energy. To understand the energy, I mean, simple harmonic motion is repetitive motion, okay? Pay attention. Simple harmonic motion is repetitive motion. Why? Definitely it's a conservation of energy. Okay? It's, pay attention. It's an energy conserved system for sure, okay? It's an energy conserved system for sure. That's why it's repeating, right? Clear? For an example, for a pendulum, here it turns into gravitational potential energy. Clear? Then when it reach here, it turns into kinetic energy. Then again it turns into gravitational potential energy. Then again into kinetic energy. So it's just a conservation of energy, okay? For a spring, here, this is the center. When it reach here, it turns into elastic potential energy. Then when it reach here, elastic potential energy converts into kinetic energy. Then again when it reach here, the spring compresses, and it again turns into elastic potential energy. Then when it returns, again turn into kinetic, again elastic potential. So it's just a conservation of energy, okay? Clear? It's just a conservation of energy. So, let's take this example of a spring, okay? Let's take this example of a spring. So now this is the center, okay? Then it may reach here, again it may reach here. This is the amplitude, and this is the amplitude in other direction. This is the amplitude and this is the amplitude, okay? So now if the spring constant is k, what is the elastic potential energy here? Elastic potential energy here is half, let's write the potential energy. What is the potential energy here? It is elastic potential energy. So the potential energy there is half kx squared, which is going to be half ka squared, right? Clear? It is going to be half ka squared. Instead of x, you have a, okay? Now, what is the kinetic energy? At the end, it stops, right? At the end, it stops. Clear? So, kinetic energy is 0. Velocity here is 0. Okay? Velocity here is going to be 0. Then the total energy. Total energy is the addition of these two, right? Half ka squared. Okay? Then at the middle, potential energy is going to be 0, right? Potential energy is going to be 0. Kinetic energy, half m v squared here, and there we have the maximum velocity, right? So the kinetic energy here is, what is the kinetic energy here is half m v max squared, okay? Half m v max squared. At the end of the day, what actually happens is this potential energy converts into this, right? Clear? This potential energy converts into this, right? Nothing else could happen here, right? What actually happens is this potential energy converts entirely into kinetic energy. So this potential energy I had here, it is going to be equal to the kinetic energy here, right? Clear? It stores a certain energy. When it extends, that turns into kinetic energy anyways, right? Clear? That turns into kinetic energy anyways. Then what is the total energy? What is the total energy? Again, 0 plus this half k squared. Okay? Then at this end, at this end, at this end, again, potential energy is half k squared. Why? It is compressed by A. It is compressed by A. So the potential energy is half k squared. And the kinetic energy is half, sorry, kinetic energy is 0. At this end, it's going to stop, right? At this end, it's going to stop. So the kinetic energy is 0. So the total energy is again half ka squared. Okay? Clear? So whatever happens, your energy graph would look like this, okay? Your energy graph would look like this. This is plus A. This is plus A. This is minus A. Okay? Potential energy. Sorry, let's start with kinetic energy, 0 here. Kinetic energy is 0 here. Kinetic energy is maximum at the middle, right? So the kinetic energy graph would look like this. Okay? Kinetic energy graph would look like this. Clear? Then what about potential energy? Potential energy is maximum here. Potential energy is maximum here. Okay? Then it reaches 0 towards the center. Clear? Then it reached a 0 towards the center. Potential energy turns into 0. Then at the other end, again it reaches its maximum. At the other end, again it reaches it to its maximum. Clear? This is what you're going to get. Okay? So this is kinetic energy. This is kinetic energy. And this is potential energy. Okay? This is kinetic energy. And this is potential energy. Got the idea? And the total energy? Whatever happens, the total energy is going to be a constant. Okay? Whatever happens, the total energy is going to be a constant. And here, since kinetic energy is 0, potential energy and total energy is equal. Here, since potential energy is 0, kinetic energy and total energy is equal. So, anywhere, if you add these two, you will get this level. Anywhere, if you add these two, you will get this level. So, the total energy is going to be this. Okay? This is the total energy. Okay? This is the total energy graph. Okay? This is also included in your tute, but if you need, like, write some points or just try to write this quickly on your book for the sake of completion, but later prepare a proper note. Okay? Yeah, about the exam, it's not going to be this week, it's going to be the next week. Okay? Okay, so next week you have the exam as usual. I think on Thursday morning. You will get until the end of mechanics. Okay? Until the end of mechanics. I think the week after that is going to be a holiday, I think. Okay? You're going to get 1 week for New Year. So the next week it's an exam. Okay? That's right. Okay, Thursday and Saturday, something like that. Okay. We'll put the schedule. Okay? Okay. Okay. So one more graph, like that we actually know. Okay. That we actually know. It is the acceleration and displacement. This should be the first graph that I draw. Okay. It's in the first page, I think. Okay. It's in the first page of your extra tute. This should be the first graph I draw. So we know that the equation is A equals minus kx, right? That is the basic fundamental equation, right? A equals minus kx. So it should look like this, okay? Clear? Acceleration and displacement graph. A equals minus kx. So it should actually look like this, right? Okay. So moving forward. Another concept. Okay. It's included in the first page of your extra tute, okay? Another concept, this angle that we turned, that omega t, pay attention, these things are included. Everything is included in a more organized manner in this extra tute, okay? Clear? I just teach whatever the way I need, okay? But I mean, things are more organized in your tute, okay? So don't worry about a note. You can go home, read the extra tute, put it onto your book, then you will have a perfect note in that area, okay? So don't worry about the note, just focus on learning, okay? Clear? So, like, pay attention. So, this angle of rotation, theta, we call it the phase, okay? Angle of rotation, theta, we call it the phase. About this phase, things are included in the page 3 of your main tute, in the book. In page 3, you can see about the phase. These things you don't have to write, okay? I mean, pay attention. Today only we are going to use something like this. Everything else is included in your main book, okay? Everything else is included in the main book. Today only we are using an additional tute because I need you to write them on your book, okay? Then later, from next week onwards, we are moving to the book. Okay, so what is this phase? Pay attention. Pay attention. What is this phase? Phase is the angle, phase is the angle of its circular motion, angle rotated of its circular motion. That means for any simple harmonic motion, there's a circle that is connected with that, right? Okay. For any simple harmonic motion, there's a circle connected with that. Okay. And the angle of that circle, okay, angle of that circle is theta, or the phase, okay? Clear? So if something is starting like this, starting here, if something is starting here, phase is going to be, starting phase is going to be 0, okay? Starting phase is going to be 0, okay? If something starts from 0, starting phase is going to be 0, okay? Clear? It's going to start from 0. Sometimes things have a starting phase, okay? Sometimes things have a starting phase. That means a simple harmonic motion can start from a random alpha angle. A simple harmonic motion can start from a random alpha angle, then keep rotating, okay? Then keep rotating. In that case, started at alpha, then the remaining part is omega t, right? Started at alpha, and the remaining part is omega t. So the phase here is alpha plus omega t, okay? Clear? Then, okay, then if two things are, pay attention, phase we usually compare in different simple harmonic motions. That assume that there are two simple harmonic motions. One can have a large amplitude and the other one can have a small amplitude, okay? But we call them, okay, we call them simple harmonic motions. Two simple harmonic motions with equal phase if they are rotating together. That means if their angle is always same. If the angle is always same. So these two are moving as two equal phase simple harmonic motions, okay? That means if I draw the displacement time graph of them, one guy will have a smaller amplitude and the other one will have a larger amplitude. Clear? One will have a small amplitude and other one will have a large amplitude, but the behavior will be same. That means at 0, both are at 0. So if this is the smaller one, the behavior of the larger one would be like this. Okay, the amplitudes may be different, but the behavior is same. When they reach the peak, both reach the peak together. When they reach the 0, both reach the 0 together. When they reach the bottom, both reach the bottom together. Clear? Okay. So these are two simple harmonic motions with equal phase. Okay. Then two simple harmonic motions with 90-degree phase difference. Let's take two simple harmonic motions with the same amplitude for this. Two simple harmonic motions with 90-degree phase difference. That means when one guy is here, other one is here. Their gap is going to be 90. Then when it rotates here, other one is going to rotate here. They are going to maintain a 90-degree angle always. Okay. So in that case, if one graph looks like this, if one graph looks like this, if one graph looks like this, okay, so other one will be shifted by, if I draw things with the phase, other one should be shifted by, this is one full rotation, right? This is one full rotation, right? So that means one full rotation means 2 pi radians, right? 2 pi radians. One full rotation means 2 pi radians, right? One full rotation means in the circle it is 2 pi radians. Okay. So if that is the case, if we break it into 4 equal parts, this is going to be pi over 2, this is going to be pi over 2, this is going to be pi over 2, and this is going to be pi over 2. Okay, clear? Clear? The simple harmonic motion broken into 4 parts. So if there's a 90-degree phase difference, 90-degree means pi over 2 radians, right? 90-degree means pi over 2 radians. That means the graph is going to be shifted by pi over 2. Okay, the graph of the other one would look like this. It will be shifted by pi over 2. Clear? It will be shifted by pi over 2 like this. So the graph would look like this. Okay, the graph would look like this. Clear? Got the idea? The graph would look like this. The exact same graph shifted 90 degrees. Clear? Exact same graph shifted by 90 degrees. This point here, this point here, this one here. Exactly same graph shifted by 90 degrees. Then if things are in opposite phase, if there are two particles moving with an opposite phase, what is the meaning of that? What is the meaning of an opposite phase? It's like this. Pay attention. When one guy is here, other one is here. Okay? When this one reach here, it's at the opposite. When it is here, the particle is at the opposite. Okay? Clear? So they always maintain a 180-degree difference. This is what we call the opposite phase. Okay? This is what we call the opposite phase. They always maintain a 180 phase difference. Okay? Clear? So in that case, the displacement time graphs would look like this. This is for one guy, and for the other one, it is exactly opposite. For the other one, it is exactly opposite. This is what we call the opposite phase. Okay? Clear? This is an opposite phase graph. Okay? So main theory points related to simple harmonic motion is over. Okay? All the main theory points are over. Now we are going to do some questions, then move into actual simple harmonic motions. Actual simple harmonic motions means we are going to analyze this behavior of an actual pendulum. We are going to analyze this behavior of an actual spring. Okay? We are going to analyze the behavior of different practical simple harmonic motions. Okay? Clear? That is the next part we have to do. So let's go to exercise 1. Exercise 1. Question 2. Question 3. 4. 8. And 9. Try them. I'll give you the interval. Be here by 5:45. Be here by 5:45. And do these questions, okay? Be here by 5:45 and do these questions. And online students, if you are not in the groups, okay? Online students, if you are not in the groups, send a message to this number, not 76. Send a message to this number if you are not in the group. And if you need to get the tutes delivered, send a message to this number. To get the tutes delivered, send a message to this number. If you need to get the tutes delivered, send a message to this number. You have to send your receipt, batch, the required tutes, the medium, the address, and the phone number. Just contact this number, then they will give you the required information. Okay. Check. Try these questions. Question 2, 3. Question 2, 3, 4, 8, 10, 9. Question 2, 3, 4, 8, 10, 9. Try these question numbers quickly. These questions are not that difficult, okay? These questions are not that difficult. I think it's enough time to try them, okay? Question 2, 3, 4, 8, and 9. Okay, so let's start with the questions. Question 2. Question 2. The periodic time of an object engaging in simple harmonic motion is 0.2 seconds. Periodic time is 0.2 seconds. Periodic time is 0.2 seconds. What is the oscillation frequency of the object? So frequency is 1 over time always, 1 over periodic time. Frequency means 1 over periodic time. That means 1 over 0.2. I'm not going to write the final answers. This is not a very important question. Question 2. How much time is taken for a single oscillation? That's the whole meaning of periodic time. Time it takes for a single oscillation is the periodic time. Okay. Time it takes for a single oscillation is the periodic time. 3. How many oscillations take place in 20 seconds? So the idea is number of oscillations, it's 20 seconds and time per one oscillation is 0.2 seconds. So this is the number of oscillations. It's 20 seconds and time per one oscillation is 0.2 seconds. So this is the total then. Then the third one, what is the time? They are giving the frequency. Frequency is 100 hertz. Frequency is 100 hertz. What is the time taken for a single oscillation? Time taken for a single oscillation is t equals 1 over f, right? If f equals 1 over t equals 1 over f, which means 1 over 100 seconds. Time taken for a single oscillation. Time taken for 25 oscillations. Time taken for 25 oscillations, it is 1 over 100 seconds per oscillation. Then into 25, okay? Into 25. Then the third one, how many oscillations take place in 10 seconds? How many oscillations take place in 10 seconds? It is 10 seconds divided by, it's 1 over 100, it's 1 over 100 per oscillation, right? This is 10 seconds, this is the time per oscillation. 10 seconds divided by time per oscillation, you get the number of oscillations, right? You get the number of oscillations, clear? Which is 1000, okay? So these questions are not that difficult, so I'm going to quickly pass through them, okay? I'm going to quickly go through them, okay? Then the next one, question 4. Next one, question 4. Quickly write this. And if you need me to repeat something, just let me know, okay? I'm just quickly going through the questions because these are not that difficult questions, okay? And not that important either. Next, the displacement time graph is given. The displacement time graph is given. This is the time, this is the displacement. So this is the displacement time graph. This is the displacement time graph. And this is 0.5. And this is minus 0.5. Pay attention. And the time values are 0.2, 0.4, like that. Sorry. 0.2, 0.4, then 0.6. 0.6. Okay. Then here, what is the oscillating amplitude? Amplitude is the maximum displacement. Amplitude is the maximum displacement, which is 0.5 centimeters. This is written as centimeters. So it is 0.5 centimeters. Then the second one, what is the periodic time? Periodic time means the time per one full oscillation. So it's starting here. This is one full oscillation, right? This is the meaning of one full oscillation, okay? This is the meaning of one full oscillation. So the time per one full oscillation is 0.4 seconds. Find the oscillation frequency. Oscillation frequency is equal to 1 over t, which is 1 over 0.4 per second. Okay, 1 over 0.4 per second. And this per second you can even write as hertz. Okay, this per second you can even write as hertz. Okay, moving forward, question 8. Question 8. Question 8. One. Question 8. 1. A equals minus 81 x. So can you remember they are asking the angular velocity, periodic time and oscillation frequency. Can you remember? Pay attention. Can you remember the standard equation we got by the circle? Can you remember the standard equation we got by the circle? A equals minus omega squared x format. Can you remember? This is what we got from the circle, right? Clear? After deriving through the circle, we got this one, right? So this is how we get omega from an equation like this, okay? Clear? So the standard format is A equals minus omega squared x. Here you have A equals minus 81x, which means omega squared equals 81, which means omega equals 9, right? Omega equals 9. Then this is the angular velocity. Angular velocity is always in radians per second, okay? Periodic time. So can you remember periodic time is equal to 2 pi of omega? We just derived that. Periodic time is equal to 2 pi of omega. Okay, so you can write it here. 2 pi over omega seconds. And the next one is frequency. Frequency is 1 over t. Frequency means 1 over t, which means 1 over 2 pi over 9. So we get 9 over 2 pi. Okay, we get 9 over 2 pi per second. We get 9 over 2 pi per second. The second one, an online student request for your tunes as soon as possible, ideally by tomorrow, okay? Or at least now, because we are going to deliver a set by tomorrow, and by next week again we'll send a bunch of tunes. After that it's going to be complex. After that it's holidays, New Year holidays, then we never know like how, when things will be delivered, okay? So I think only next week the services will be active. So after that we don't know. Then ideally I think by the end of New Year there will be a huge war. Okay, so we anyways the services will not be working, the fuel issues, all the problems may arise. Okay, so just get your dues now. Okay, question 2. Question 2. A equals minus 64x. A equals minus 64 Pay attention. Pay attention. A equals minus 64x. Okay. So A equals what? Minus omega squared x. So omega equals omega squared equals 64. Omega equals 8. Then you know everything, right? When you know omega, you know everything. T equals 2 pi over omega, which is 2 pi over 8. Frequency is 1 over time, 1 over periodic time, which is 8 over 2 pi per second. Question 9. Question 9. Question 9. Frequency of an object is of a simple harmonic motion is 50 hertz. Frequency is 50 hertz. Pay attention. Frequency is 50 hertz. Write down its periodic time. Write down its periodic time, angular velocity, and the relevant simple harmonic motion equation. Okay. Pay attention. So frequency is 1 over periodic time. So the periodic time is 1 over frequency, which is 1 over 50. Okay. Which is 1 over 50 per second. Per second. Then that is the periodic time. Angular velocity omega equals 2 pi f, right? We can write 2 pi fy. Omega equals 2 pi over t, and 1 over t is equal to f, right? 1 over t is equal to f. So we get 2 pi f. Frequency is given as 50 hertz. Frequency is given as 50 hertz, 2 pi f. Then next one, this is the angular velocity, which is 100 pi, Then the simple harmonic motion equation. So the simple harmonic motion equation is A equals minus omega squared x, right? So that's what we call the simple harmonic motion equation, okay? Clear? So we get A equals minus omega means 100 pi. Omega means 100 pi. Okay? Omega means 100 pi squared x. Okay? Clear? This is the equation. This is going to be the simple harmonic motion equation. Okay? So you somehow find omega, then you have the fundamental equation of this simple harmonic motion. Okay? Clear? So let's move forward. Let's move forward. Okay. Periodic time is seconds. Frequency is per second. Yeah, thank you. So this is in seconds. Thank you. Here we got the periodic time, right? Yeah. So it's in seconds. Okay. Then the next part. Okay, moving forward. Let's move forward. Now practical stuff. That means pay attention. Pay attention. Let's understand some practical simple harmonic motions, okay? Pay attention, stop talking. Let's understand some practical simple harmonic motions. What are practical simple harmonic motions? For an example, take the motion of a mass connected to a spring, okay? So if we have to understand this kind of a simple harmonic motion, what do we need? To perfectly understand a simple harmonic motion, you need two things. One is the amplitude and other one is omega. Why? Can you remember all the equations were with these two, right? A sine omega t, A cos omega t, V equals omega A squared minus V equals omega A squared minus x squared. Okay, all these equations, okay, all these equations are with what? With omega and a, right? X is always unknown, okay? So it's, I mean, to understand, to perfectly understand everything, to draw all the graphs, to have 100% clarity about everything, what you need to know about a simple harmonic motion is it's a and omega, right? These two things. So amplitude, definitely they have to give. Why? If you stretch this for 5 centimeters and release, then the amplitude is going to be 5 centimeters. If you stretch this for 1 millimeter and release, then the amplitude is going to be 1 millimeter. Clear? Okay. So amplitude should be given anyways. Okay. So it's not a big deal. Amplitude, just they have to give it in the question. Okay. Clear? I mean, it's just what you do. You stretch this for 5 meters and release, then it will move 5 meters, right? Clear? So amplitude can be directly taken by the question. Okay. What about omega? If the spring constant is k and the mass is m, okay, if you stretch this by a distance of x, if you stretch this by a distance of x, what will be the force pulling this backwards? What will be the force pulling this backwards? F equals ma, okay, and the force is going to be kx, right? It's a spring. So spring constant into stretched length is going to be the force, right? F equals kx, clear? Equals ma. Mass is m, acceleration is a. Okay? Kx, it is the force, equals ma. Okay? Then I get acceleration equals what? K over m. Acceleration is equal to k over m x. Clear? Acceleration is equal to k over m x. Then you can put the minus mark. Why? I mean, this I just wrote with the magnitudes, but now when I look at the system, displacement is in that direction, acceleration is in this direction. Why? Force is in this direction. Force is in this direction, at the same time displacement is in that direction. So they are opposite. Force and the displacement are opposite. Clear? That means the acceleration and the displacement is going to be opposite. Clear? So you can just put the minus mark, okay? You can just put the minus mark. Okay? Now you know omega. Why? This is the standard format. A minus something into x. And what is the standard format written using omega? This is the standard format written using omega, right? Then omega squared equals k over m. Then omega equals square root k over m. Okay? Clear? So these things are included in the extra tute given today. These things should be written on your book. Why? These proofs you have to do at least once, okay? You have to do at least once by your hand, since it takes a lot of time for this, okay? Since it takes a lot of time for this only, I have given it in the tute, extra tute, but you definitely have to write them, okay? You definitely have to write them in the 5th page of the extra tute. In the 5th page of the extra tute, you can find this, okay? Clear? There are some other facts in that tute. I'll do them later, okay? I'll do them later when I'm doing questions. Some stuff are not in the syllabus. I mean, force is negative because, I can't tell what is positive and what is not negative. All I know is x is in that direction, then f is in this direction. So they are opposite. So when you connect two opposite vectors, there must be a minus sign, okay? When you connect two opposite vectors, there must be a minus sign, okay? Pay attention, last rows. There, okay? Pay attention. There must be a negative sign if two vectors are in opposite direction, okay? That's why I put a negative sign. I don't know what is positive and what is negative. For that, I need a positive direction. I have to choose a positive direction for that. But all I know is when x is in this direction, f is in this direction. They are in opposite directions, right? Okay, quickly write this. If you need, you can write along with me. But I'm not going to give separate time for that, okay? Because things are given. Okay. Okay, the next one, pay attention. And the behavior of a vertical, pay attention. Behavior of the vertical spring is also the same, okay? Same omega. Behavior of a vertical spring is also the same. So it's same omega. Same omega. Clear? Pay attention. Don't we have to consider gravity here? As I mentioned, see, I'm telling that we have the same omega here and here, okay? I'm telling that we have the same omega here and here. Don't we have to consider gravity? No, why? The reason is, at the center of oscillation, pay attention, at the center of oscillation, they are already balanced. At the center of oscillation, they are already balanced. Let's take this as the center of oscillation. If this is the center of oscillation, they are already balanced. That means here we have a certain mg, here we have a certain kx, okay? It's already balanced. So they are anyways already neutralized. The weight is already neutralized, okay? Weight is already neutralized by the kx value at the beginning. That I'm not going to take as the x value of the simple harmonic motion. I take this as the balance point. I take this as the balance point, okay? Pay attention. I take this as the balance point, and whatever the x value I give after that, it's going to be an additional kx. This kx part is balancing mg, the initial x dash, okay? At the beginning it's balanced. Whatever the displacement I'm going to give after that, it's going to act as a separate kx, right? I mean, what actually happens is, when I write f equals ma to this guy, initially also it's stretched by x dash, okay? So there I have kx dash equals mg, okay? There I have kx dash equals mg. Then when I take this as the center of oscillation, okay? I take this as the center of oscillation. Then when I give it a displacement of x from here, force is going to be, when I write f equals ma, force is going to be what? K x plus x dash. It's going to be k x plus x dash, the total stretched length. The total stretched length is going to be k x plus x dash, okay? Total stretched length is going to be k x plus x dash minus mg equals ma. Minus mg equals ma. Clear? Minus mg equals ma. Then what I get here is kx plus kx dash minus mg equals ma. Okay? Then anyways this kx dash and mg cancels out, okay? Anyways this kx dash and mg cancels out. See? Because they are equal. Then what I left with is kx equals ma, which is equal to a equals k over m x, just as before. Clear? Then I put the minus sign. Why? When x is downwards, the additional force is upwards, okay? Clear? When x is downwards, additional force is upwards, which means the acceleration is going to be upwards, okay? Clear? When x is downwards, additional force is going to be upward. Clear? Which means the acceleration is upwards. Got the idea? So weight anyways doesn't affect the motion, okay? This is not included in the tune. I mean, if you need, you can write things, okay? I'm not going to give separate note for this kind of stuff because it's not necessary, okay? It's not necessary. If you know how to find omega, that's all, okay? Clear? But I mean, everything is written in that extra tute, okay? So if you like, you can write things as a note, everything in the extra tute. If you like, you can convert them into your note. Okay, next example. Next one. A simple pendulum. What is a simple pendulum? A simple pendulum is something like this, that oscillates like this. Pay attention. This is a simple pendulum. So at the beginning, we actually don't know. At the beginning, we actually don't know whether this is a simple harmonic motion or not, okay? We don't even know whether this is a simple harmonic motion or not, okay? That also we have to figure out, okay? That means, after applying F equals ma to this spring, okay? After applying F equals ma to this spring, if I didn't get this format, then it is going to be just a harmonic motion, not a simple harmonic motion. Anything can be a harmonic motion. Clear? Harmonic motion means something repeating, that's all. Okay? So, if when I apply F equals ma and when I try to derive this, if I get something different, okay? If I get something different, it's just a harmonic motion, not going to be a simple harmonic motion. If it is a simple harmonic motion, you should be able to get the proper one, okay? Get the proper equation. Clear? That is the idea. So, in this case, let's assume that, so one knot is, this is going to be a simple harmonic motion only for very small angles, okay? This is going to be a simple harmonic motion only for very small angles, but just for the sake of the proof, I'm gonna mark a bit larger angle. So now, this is mg. This is the center of oscillation. This is the center of oscillation. If this angle is theta, then this is theta. If this angle is theta, then this is theta. Then what is the component of force in this direction? Mg sine theta, right? Component of force in this direction is mg sine theta. That's what brings this backwards, okay? That's what brings this backwards. Got the idea? So now the displacement from the center is x. Displacement from the center is x. Okay? Displacement from the center is x. And we have mg sine theta in the opposite direction. Okay? Now, if I apply F equals ma, in backward in this direction, I get mg sine theta. I get mg sine theta equals ma, right? I get mg sine theta equals ma. Okay? Mg sine theta equals ma. Okay? Then, now there's a problem. Here I have mg sine theta, here I have ma, then m cancels out, then I get a equals g sine theta, okay? I get a equals g sine theta. This looks nothing like the fundamental equation of a simple harmonic motion, right? This doesn't look like a fundamental equation, right? Clear? This doesn't have that pattern of a fundamental equation. It should have x there, okay? So we can't use this and tell that this is a simple harmonic motion. We have to bring other factors in, okay? We have to somehow bring this guy into this equation, okay? For that to happen, this has to be a small angle, okay? For that to happen, this has to be a small angle. Why? When the angle is small, sine theta is equal to theta radian. Can you remember? For smaller angles, theta radians equals sine theta equals tan theta. Okay? For smaller angles, theta radians equals sine theta equals tan theta. Okay? These three are equal. Okay? So based on that, sine theta I can replace by theta. Now what I can do is theta is radian theta, right? What is the definition of radians? Definition of radians is if the length of this string is L, x over r. Can you remember? Definition of radian theta is x over r. Can you remember? Definition of radian theta is here, then x over L. So I'm going to get theta as x over L. Then what? Then I have something like this. A equals G over L x. A equals G over L x. A equals G over L x. Now x is in this direction, acceleration is in this direction, right? As usual, x, the displacement is in that direction from the center, acceleration is in the opposite direction, right? Clear? Acceleration is in the opposite direction. So you put a minus mark here. Clear? You put a minus mark here. Got the idea? Now it looks like the official equation, right? It looks like what? A equals minus omega squared x. Clear? It looks like A equals minus omega squared x. Got the idea? Then what? Then omega squared equals G over L. Then omega equals square root G over L. Omega squared equals G over L. Then omega equals square root G over L. See? Now I can tell that this is a simple harmonic motion. Clear? So as a result, this works only for smaller angles. If the angle is large, I can't do this. Then I can't get this equation. So for larger angles, it's not going to be a simple harmonic motion. That means even if you give 90 degrees, to start, still it will oscillate as a, it will oscillate like this, okay? Still it will oscillate like this. But it's only a harmonic motion, not a simple harmonic motion. Clear? Clear? Still it is a repetitive motion, which means a harmonic motion, but it's not going to be a simple harmonic motion. Got the idea? Okay. So it works only for small angles. This is also included in the additional tude, but if you need to write something, write it down. A good question. What about the tension of the string? Why am I neglecting it entirely? What about the tension of the string? It's a good question. It's not going to do anything about this motion, right? Why? If this is the center of motion, okay, I need the acceleration towards the center, right? Pay attention. I need the acceleration towards the center. And the tension is in this direction. It is 90 degrees, right? So it has no component in this direction. Clear? Tension has no component in this direction. Got the idea? That's why the tension can't do anything, okay? Tension doesn't have a component in this direction. T cos 90 is going to be 0, right? Clear? That's why the tension is neglected, okay? So now we can do some questions again. Uh, Exercise 2, question 4. Question 5. Question 5. Take this as a horizontal spring. Take this as a horizontal spring. Question 5. Question 10. Question 10. Then question 6. Start with these questions. I'll give some time to try. Start with these questions. Quickly go through the questions. Quickly go through the questions. And ask if you have any questions, okay? Ask if you have any questions. Ask questions if you have any. So if you can't do the questions, at least go through the note again and be comfortable with the theory, okay? If you are not okay with doing the question, if it's difficult to do the question, at least go through the tute again, okay? At least go through the tute again and be comfortable with theory. Within 2-3 minutes, within 2-3 minutes, I'll start the discussion. Okay, let's go to the questions. question 4. Two simple pendulums. I'm going to do each question using different methods, okay? So that you can get a better clarity about all the equations, okay? You can get a better clarity about all the equations. I mean, one question I'll try using the simple harmonic motion equations. One question I'll try using the circles, okay? Like that, for each question, I'll use a different method. Two simple pendulums of length 1 meter and 16 meter oscillate on their center of oscillations at the same phase at a certain instant. If the periodic time of the short pendulum is t, find the time taken for the pendulum to oscillate at the same phase again. Okay. So now, to start with, what is the omega value? To start with, what is the omega value? The omega value is this, right? Omega value of a simple pendulum, pay attention. Omega value of a simple pendulum is this, right? Clear? So I can get omega as root G over L. Root G over L. Okay. Then in one instance, omega 1 is root G over L. Length is 1 meter. Length is 1 meter. And in the second instance, omega 2 is root G over L. Length is 16 meters. Okay. Length of the string is 16 meters. Which is going to be G over 1. And I'll take 1 over 4 out, right? Okay. Then, of the short pendulum, the periodic time is t. So, t is equal to 2 pi over omega, right? Periodic time t is equal to 2 pi over omega. Clear? Periodic time is 2 pi over omega. Then you are going to get what? 2 pi over, what is omega 1? This, right? This. G over 1. Clear? Okay. This is t. Periodic time is 2 pi over omega, which is 2 pi over this. Which is going to be 2 pi over root G. 2 pi over root G. Then in the next scenario, t equals what? 2 pi over omega 2. Pay attention. In the next scenario, t equals, I'll take that as that's not given, right? So the new periodic time, let's take it as t dash, periodic time of the second one, t dash, it is equal to what? 2 pi over omega 2. This is omega 2. 1 over 4 root G over 1, which means 4 into 2 pi, pay attention, 4 into 2 pi over root G, which means what? 4 into, pay attention, 2 pi over root G is t, right? 2 pi over root G is t. Then here also it is going to be 4 into t, okay? It's going to be 4 into t, okay? So if this is t, this is 4t. Clear? Now there's a bunch of methods that we can use for this, okay? There's a bunch of methods that we can use for this. What are the methods? What are the methods? Pay attention. I mean, they are asking is, find the time taken for the pendulum to oscillate at the same phase again. What is the meaning of same phase? There's one pendulum oscillating like this, another oscillating like this. So they start randomly. They start at the same phase. Since their velocities are different, they move randomly like this, okay? They move randomly like this. But after a certain time, again they oscillate together. For instance, they meet together. Then again, different. Then same phase again. So time to time, they will meet in the same phase again. Pay attention, stop talking. Time to time, they will meet in the same phase again and again, right? Clear? Time to time, they will meet in the same phase, okay? Clear? So understanding the phase using pendulums is very difficult, okay? Clear? So we move to their circle. We move to their circle. So the actual meaning is there's one pendulum moving with 1 omega, which is omega 1. There's another pendulum moving with the angular velocity of omega 2, moving with the angular velocity of omega 2. Clear? Omega 2. I think omega 1 is faster. We'll see about that. So one is moving with a certain velocity omega 1. Pay attention. And other one is moving with omega 2. Okay. Then they are not, at the moment they are moving together. Since the velocities are different, one person is going to move faster and other one is slow. Other one is slow. But after a while, this one will go faster and meet this guy again, right? Clear? Then again after a while, this guy will go faster and meet this guy again. Okay, that is the meaning of meeting at the same phase. Meeting at the same phase means they meet at the same position of their circles, right? They meet at the same angles or they meet at the same positions of their circle. Clear? That is the meaning of meeting at the same point again. Clear? Okay? That's the meaning of phase. So, I mean, understanding phase is extremely difficult when it comes to the pendulum. But when you think about the circle, it's just the angle, right? Clear? So, when they meet at the same location of the angle again and again, that is equal phase, right? Clear? So, the simple idea is there are two people running in a ground. One person is faster and other one is slower. So, the question is, what is the time gap of them meeting again and again? Clear? So when the slower guy, when he runs a certain distance, faster one will move fast and meet the person again. Then again meet the person again. Clear? So for this to happen, okay, for this to happen, the idea is, for this to happen, the faster one should rotate one additional circle, right? That means when the slower one goes from here to here, faster one definitely passed this one, okay? Then to meet this guy again, he has to go one additional circle and reach here. Then only they meet, right? If you are running faster than your friend, you have to run one additional circle to meet the person again, right? Clear? So that means when the faster guy completes one full rotation, when the faster guy completes one full rotation additional to the slower one, then they meet again at the same phase. So I can convert this into what? A relative motion question if I like. I can convert this into a relative motion question if I like. Got the idea? Why? Why? What is the reason? I can tell something like this. Okay? I can tell something like this. So they will meet again. Let's think that they will meet again after time t. Okay, what is that time? That is time that time is their gap is going to be 2 pi. Relative angular velocity is omega 1 minus omega 2. Do you understand this? So the faster one should rotate one full additional circle, which is 2 pi. and their relative velocity is omega 1 minus omega 2. So you divide the relative angle by the relative velocity, you get the time they meet again. See, we can convert this entirely to a mechanics question if we want. Okay, clear? So I mean, there's a lot of ways of seeing the same question. I'm going to go through different aspects like that, so that you get a better clarity about this simple harmonic motion. Okay, see, this is one option. See, you divide the relative angle, I mean relative displacement divided by relative velocity, you get the time, right? Relative displacement divided by the relative velocity, you get the time. Similarly, relative angle means additional 2 pi angle. Okay, the faster one should go additional 2 pi divided by the relative velocity between them. Clear? Then you get the time again. Clear? This is one option. So you can tell t equals what? 2 pi. What is omega 1? Omega 1 is 2 pi over t, right? 2 pi over t. Okay, omega 1 is 2 pi over t. Then what is omega 2? It is 2 pi over the periodic time of the other one is what? What is the periodic time of the other one? It is 40, right? Periodic time of the other one is 40. So you solve this, you get the answer. Clear? This is one way of seeing this, right? 2 pi cancels out. You get 1. Here when you solve this, you get 3 over 40. Then you are going to get 40 over 3. You are going to get 40 over 3. Clear? Clear? You are going to get 40 over 3. This is one option actually. Okay? This is one option. There are many other options that you can use to get the answer. Clear? So the question simplified is, pay attention, one person is running with an angular velocity of omega 1, other person is running with an angular velocity of omega 2. Then what is their relative angular velocity? Omega 1 minus omega 2. Clear? So in their relative world, one person is stationary, other person is running. So the person who's running should rotate additional 2 pi angle to reach here again. So the relative angle is 2 pi, relative velocity is omega 1 minus omega 2. This gives you the time that it takes for them to meet again. Clear? Clear? This is one option, okay? This is one option. What are the other options? What are the other options? Another option, you can write things later. Another option is, pay attention, another option is frequency of meeting each other. That means, think this, one pendulum is faster, other pendulum is slower. Okay? That means one person is running faster, other person is running slowly. Frequency of the faster one is F1. Frequency of the slower one is F2. This frequency difference would be the frequency of them meeting each other again, right? What is the meaning of that? Frequency is, pay attention, frequency means how many rounds per second. Think the faster person runs 5 rounds per second. Faster person runs 5 rounds per second. Okay? Slower person runs 3 rounds per second. How many times will they meet on the way? 2 times, right? When one person runs 2 rounds in a second, if the other person runs 5 rounds in a second, okay, they will meet 3 times, right? They will meet 3 times, right? This is not Waves and oscillations or mechanics, it's common sense, okay? Clear? Okay? When one person runs 2 rounds, at the same time, if you run 5 rounds, on the way you will meet the person 3 times, right? Clear? So frequency means how many rounds per second or how many oscillations per second. So if this is the number of oscillations of the faster one, if the number of oscillations of the slower one, the frequency of them meeting each other would be the difference of these frequencies, right? Clear? Clear? So you can tell F is 1 over T, right? 1 over T1. F2 is 1 over T2 equals F is frequency of them meeting each other, which means 1 over the time it takes for them to meet each other. Clear? Frequency of them meeting each other is equal to 1 over time it takes for them to meet each other. Okay? So this is another option. See? Here also T1 is T and the periodic time of the other one is 4T, which is equal to 1 over T, which is going to be, when you solve this, what? 4T over 3. See? There are thousands of ways like this, okay, to handle the same question. Okay? Okay? So it's just about being much familiar with the equations first, okay? You have to be familiar with the equations first, then connect it with your common sense, okay? You have to be more familiar with the motion, okay? Pay attention. To be okay with any concept in physics, the first thing you should do is you have to be more familiar with that concept, okay? Clear? That's why I'm telling the same thing in different ways, okay? First of all, it should be in your common sense, okay? So when you first learn a concept, it's not in your common sense. It's something very alien. Then we do different questions and try to connect it with our common sense. What is the meaning of equal phase? Like that, we try to connect it with our common sense. Then only we are familiar with that theory. Then only we can do questions properly, okay? So there are different options like this. I mean, if you are not capable of doing these questions, it's okay. I mean, it's the first time you are seeing questions like this. So it's okay to find them difficult, okay? Okay. Let's move forward. Quickly write this. Question 5 next. Question 5. Okay. Let's move to question 5. A 2 kilogram mass. There's a mass of 2 kilogram. A 2 kilogram mass which is hung on the light helical spring engaged in a simple harmonic motion with an amplitude of. Amplitude is, pay attention, 10 centimeters, which is 0.1 meters. Spring constant K is 200. Spring constant K is 200. write an expression for maximum kinetic energy in terms of K and R. So here they have given us the amplitude as R. They have given us the amplitude as R. So as you know, pay attention, we have the maximum potential energy when it is stretched a maximum. Here the amplitude is given as R. Clear? So we have the maximum potential energy here, right? So the question is, they are asking for the maximum kinetic energy. Okay. So now you know the concept, right? Now you know the concept. That means this is the amplitude. This is the amplitude. This is the energy we have here, half kr squared. This is the maximum potential energy. When it is stretched to its maximum, it has the maximum potential energy. Then it's gonna return back to the center position. At the center position, here the kinetic energy is 0, right? Here the kinetic energy is 0. At the center position, it's not stretched, which means its potential energy is going to be 0. Its potential energy is going to be 0. That means its kinetic energy is equal to half kr squared. Why? The potential energy stored here turns into kinetic energy when it reaches here, right? Potential energy stored here turns into kinetic energy when it reaches here. Clear? So I can write this is the maximum kinetic energy, right? We have the maximum kinetic energy at the middle. It is equal to the maximum potential energy. Why? Maximum potential energy we have here converts into kinetic energy when it reaches the middle point, right? Clear? It's just an energy conservation, okay? So the maximum kinetic energy, Ke max, is going to be equal to the maximum potential energy. Maximum kinetic energy is going to be equal to the maximum potential energy, which is equal to what? Half kr squared. Half kr squared. Half kr squared. Clear? Next one. Next. What is the displacement when kinetic energy is equal to the potential energy? Pay attention for this. We need what? We need the displacement when kinetic energy is equal to the potential energy. This you have to understand properly. Pay attention. This is a spring. This is the maximum potential energy. This is the maximum kinetic energy, which is equal to total energy. Do you understand this? In the potential energy and kinetic energy graph of a simple harmonic motion, this is the behavior of kinetic energy. Sorry, this is the behavior of potential energy. This is the behavior of kinetic energy. And at any point, the total energy is same, right? Clear? Clear? So here, when we have the maximum potential energy, kinetic energy is 0. Which means total energy equals what? Total energy equals here maximum potential energy. Total energy equals maximum potential energy. Clear? At the middle, potential energy is 0. Here see, maximum kinetic energy equals total energy. Got the idea? That means in a simple harmonic motion, maximum kinetic energy is always equal to the maximum potential energy is always equal to the total energy. Got the idea? So it's simple now. Why? Let's assume that this required thing happens at the displacement of x. Let's assume that here kinetic energy and potential energy is equal, okay? That's what they ask, right? Let's assume that a displacement of x, at a displacement of x, kinetic energy and potential energy becomes equal. So here, I can easily get the potential energy. Why? What is the potential energy? Half kx squared. That's our spring functions, right? Half kx squared. That's all. Okay. What is the kinetic energy here? I can write at any point total energy equals kinetic energy plus potential energy, right? Total energy equals, at any point, total energy equals potential energy plus kinetic energy, right? And the total energy is equal to half kr squared or half ka squared. Total energy is equal to the maximum potential energy, which is equal to half kr squared. Now the potential energy I have is half kx squared plus kinetic energy I have to find. So I get the kinetic energy. What is that? Half k r squared minus x squared. Clear? So this is the kinetic energy and this is the potential energy. So we need x when potential energy and kinetic energy is equal. So what we do is kinetic energy equals potential energy. This is kinetic energy half k r squared minus x squared. What is the potential energy? Half kx squared. Half kx squared. Okay. Then k cancels out. Half cancels out. We get r squared minus x squared equals x squared. R squared equals 2x squared. Then x equals r over root 2. Clear? X equals r over root 2. Okay. So this is where we get the potential energy equal to the kinetic energy. Clear? So r was given. Amplitude was 0.1 meters. Amplitude was 0.1 meters. So this happens when 0.1 over, this happens at 0.1 over root 2 meters. This happens at 0.1 over root 2 meters. Clear? Okay. Next. These are the answers for part A 1 and 2. Part A 1 and 2. This is 1. This is 2. Okay. B. Find the oscillation time relevant to the simple harmonic motion. So what was the omega value? What was the omega value we obtained for a spring? What was the omega value we obtained for a spring? It was root k of m, right? Pay attention. It was root k of m, right? You don't have to derive them, okay? You don't have to derive them. You can use them directly. This we derived, right? Omega equals root k of m. So you can get the answer. Omega value is spring constant is 100. Spring constant is 100. M. The mass is given as 2 kilograms, right? Sorry, K is 200. K is 200. K is 200. And the mass is 2 kilograms. This is going to be 10, right? This is going to be 10 radians per second. This is omega. Then the oscillation time means periodic time, which is 2 pi over omega. Pay attention. Which is 2 pi. Omega is 10, which is pi over 5 seconds. Pi over 5 seconds. Next, pay attention. Next. 2 kilogram, find the maximum velocity and the maximum acceleration obtained by 2 kilogram. Maximum velocity. Can you remember the maximum velocity? V equals A omega, right? Can you remember this? If you can't remember, use this equation. V equals omega A squared minus x squared. Can you remember this equation? So lower the x, higher the v, right? Lower the value of x, higher the value of v, right? So when x equals 0, I get A omega. Velocity equals A omega. Clear? When x equals 0. So what is the amplitude? Amplitude is, it was given, right? 0.1 meters, right? Amplitude is 0.1 meters. Omega is 10. Okay? Omega is 10. Okay? Then you are going to get 1 meters per second. 1 meters per second. Maximum acceleration, if I get the magnitude of the acceleration, it is A equals omega squared x. It is A equals omega squared x. Then when do I get the maximum acceleration? When x is maximum, right? Maximum value of x is the amplitude, right? Maximum value of x is the amplitude, right? So I get the maximum acceleration. I get the maximum acceleration at omega squared amplitude, which is equal to omega is 10. Omega is 10 squared. This is 10 squared. Amplitude is, what is the amplitude? Amplitude is, it was 0.1, right? Amplitude was 0.1. This is going to be 10 meters per second squared. 10 meters per second squared. Clear? I mean, I'm not going to go through a bunch of questions like give 5 pendulums and find the periodic time of them. It's useless, right? So I'm starting with a bit difficult questions, okay? Clear? There's no point of giving 5 pendulums, giving the length and asking you to find the periodic time. Then give 5, 6 springs and asking you to find the periodic time. It's not a useful thing. So that's why I started with the difficult questions. So it's okay not to be comfortable with the questions, okay? It's okay not to be able to do the questions. If you understand after the explanation, then it's okay. Clear? So try the questions to a certain level. Next week we'll continue the questions. Next week we'll continue the questions, then move forward, okay? We'll move forward with the waves. And new students, stay after the class and join the group. And if there's any missed recordings, missed parts, previous parts, request for them, okay? So new students, stay after the class and ask our people. They will add you to the group, give you the required tunes, and we can discuss what to do for the things that you have missed, okay? So new students, talk after the class, okay? Yeah, and the exam will be next week. Thursday morning is the fixed time. Pay attention. Thursday morning is the fixed time. As usual, we'll give another time for the students who missed that exam due to like reasonable issues, okay? Clear? We'll give a separate time for the students who missed the exam due to reasonable issues. Yeah, that's mainly about that. And the heat lesson or the next lesson that we are planning to do for the English medium students will be starting within a week, okay? We'll put that information in the group, okay? Yes, so that's all for today. And thank you. You know what happened to the match, right? You can't host events with more than 100 people. I mean, we went to get like for the New Year of at Sysygy Ratnapura, we had to cancel that too. The New Year celebration. There's like 1,000 or 3,000 students participating, and can't get sound permission for that. The government has requested not to provide electricity to events hosting larger than 100 people. But the government gazette was after 8 p.m. But at the police stations and all, when we try to go to get the sound permits, then it's a different story. They're asking us to cancel events like the whole day. I mean, I mean, it's anyways the law in Sri Lanka. I mean, Wednesdays we can't do class, but from next week onwards, I'm doing classes on Wednesday. So like that, we can skip the rules, but I mean, it's not a very good time to skip the rules. Yes, I mean, from next week, Wednesday onwards, we are starting classes. Everywhere the classes are happening. So like that, we can skip that rule too. But I mean, it's not a very good time to skip all the rules. Okay, one per time. So that's why that was the reason. I mean, there's nothing, no other specific reason to cancel the event. We had to cancel. We can't get sound permits to do the event. That's a problem. And I don't think that things will be resolved any sooner. We'll see. We'll see about that. Thank you.